So in this video, I want to give you 3 different methods you can use using your data from Tracker to get the acceleration of an object that is moving at constant acceleration. The way we're going to do this, we're going to do a little experiment here in this Minecraft world that I set up, where I've got a piston that has just released a sand block. Sand, of course, obeys gravity in Minecraft, so the sand block is going to fall down against the wall here. I've already got my X and Y axes set up here, and I've set the scale for 1 meter to be a single block. I believe that's the scale that Minecraft uses, but the actual number doesn't really matter since this is Minecraft, not the real world. It's really the technique of what you do once you have a graph that I want to highlight for you in this video. So we're going to do our Control-Shift-Click here, and I need to pay attention to the template that I have because you notice that my template has a little bit of the sky background. Well, it's not going to have sky background farther down below here. So let's zoom in on this, and we'll need to basically decrease the size of the window that it's looking for. So let's decrease the size of this circle here. I can even make it a little bit elliptical to capture more of the sand block. Really what I want it looking for is the color of the sand block, which I don't think occurs anywhere else in here. All right, so let's click on search here to get going. All right, we followed it past the transition point there. It's a couple kinks every now and then, but that should be okay. And then finally, my sand block drops here. We had a pretty significant drop there. That's a bit odd. But point being, I've got a pretty decent graph here. You can see this thing makes almost a parabola. There's a couple of kinks here, probably due to some video rendering issues or something like that. And that will happen, of course, in your experiments as well. But overall, I've got a parabola on the position graph, which is exactly what I expect to have when I have constant acceleration motion. And so we're going to examine 3 different ways to get the value of the acceleration from this motion. So first, let's start with the position, because that's the first type of graph that you encounter. What you need to do is right-click on this and click on Analyze. Analyze brings up this data tool window that it gives you a little bit more interactivity with the data here. So we're going to click on the Analyze button here, and we're going to click on Curve Fits. Curve Fit is what we're interested in doing when we are trying to determine what equation governs this graph. So we're going to click on Curve Fits. The default option is a line because about half of the time in physics you're going to want a line graph. This, of course, is not a line. This is pretty clearly a parabola. So the line that it's attempting to fit does not fit very well. And it tells you that with this RMS, root mean square deviation, that's this RMS dev, we want this to be a small number. And this is a pretty big number. So what we're going to do is click on the fit here. We want to pick a different type of fit. Cubic is too advanced. That's something to the third power. That's more advanced than we need. Exponential is not the correct answer here because exponential means e to the t, or e to the independent variable. So we're going to go down here. We're going to click on parabola because that's what we have. So it's a polynomial of degree 2. So we'll click on that. And you can tell right away from the graph that we have a pretty good fit. In fact, the polynomial fit is doing a pretty good job of ignoring these blips, of being unaffected by them, and so we can kind of get an idea of where the parabola is supposed to be going in the middle of those blips there. What you want to pay attention to at this point is the fit equation inside this little cell here, because this is telling you what equation the analysis tool is using to fit the data. So what's going on in the computer's memory is it's playing around with these coefficients A, B, and C until it gets the parabola to fit the data in the best way possible. In other words, until it gets the lowest RMS deviation, which again, right now is very small. So we've got 3 coefficients to worry about. We have A, B, and C. A is the thing multiplying t squared, B is the thing multiplying t, and C is a constant. So you can think of these as C being the sort of offset here. So we are starting up at 25, so C needs to equal 25. That's just the y-intercept, basically. B, on the other hand, is the initial velocity of the object. In this case, it's a -4 because the sand block was moving a little bit when I first started the video capture, and that's okay. But that's basically the initial slope here, the initial value of the velocity as the block begins to fall. And then A, you might think that A is the acceleration. A is actually half of the acceleration. The reason there's a half in there is because of some calculus reasons. If you're familiar with calculus, then you know that that half is there because of the integration. If you're not familiar with calculus, then don't worry. Just take my word for it or look it up in a textbook that the thing that multiplies t squared is 1/2 of the acceleration. So it's a little bit confusing here because it's a capital A, acceleration is a lowercase a, but just if we take 2 times this number, we'll end up with the acceleration. And in fact, 2 times this is going to give us a -10, which is about the same acceleration that we have here on Earth of -9.8 meters per second squared. That's our acceleration due to gravity near the surface of the Earth. And so Minecraft actually does a very good job of simulating free fall motion because it's got about the same value of acceleration due to gravity that we have. So if I were a physics student and I were studying this, I would want to make a note of that acceleration value. So I'm just going to open up a little notepad and say that the acceleration from the position graph equals, I'm just call it -10. I know this thing goes out to several decimal places, but unless you are, trying to study Minecraft on behalf of NASA for some reason, you can really get by with just a couple of significant digits. Unless you're really trying to split hairs, calling this a -10 is perfectly fine. At least in my class it is. Maybe I should give that caveat. In my class, this is -10. Okay, so we've analyzed the position graph. Let's go back over here and let's do the same thing with the velocity. So I'm going to shift this over to the velocity y component. And now if this were a nice constant acceleration motion, this thing would be linear. And except for, the ups and downs, it kind of follows a linear trend. So let's right click on this, click on Analyze again. And now Tracker is confusing us a little bit because now it's trying to put both of these sets of data on the same graph. So here's our position graph from before. Here's our velocity graph from now. So what we're going to do is over here where we have the Y column, we're going to deselect this so that we don't have it on the graph anymore. So you can't compare position with velocity. That they have different units. That the numbers don't correspond to each other. So you don't want to display those on the same graph because it'll confuse yourself and your reader of your lab write-up. Now for this one, we expect this to be linear. So if our position graph is a parabola, then we expect the velocity graph to be linear. So we're going to shift the fit from parabola over to line. So we're going to change the fit over to line. This is a lot simpler. It's only got 2 parameters, right? Y equals mx plus b. So we have a slope, we have an intercept. Again, in this case, our intercept, b, is going to be the initial velocity, because that's the velocity of time t equals 0. We get an initial velocity of about -3.6. That's about what we had on the acceleration graph, which is good. And then here I've got the slope here is the acceleration. So this time there is no multiplying by 2 because we don't have that calculus extra step coming in here. And so we get an acceleration, a slope of about -10.5. This is being multiplied by 10 to the first power. So anytime you see this capital E, that just means times 10 to the. So this -1.054 E1 is -1.054 times 10 to the 1. So what that means is this number is actually, you guessed it, -10. So I come over here to my notepad and I say that the acceleration from the velocity graph is equal to about -10. And again, if you're really worried about splitting hairs, you could say that one is -10, one is -10.5. I might even put in parentheses here -10.5 and we'll check on later. Just in case. But generally, that's a good match, right? For an introductory physics course, that's a very good match. We're not trying to find the Higgs boson here. We're just dropping sand in Minecraft. Okay, and then we have one more type of graph we can look at. There's the acceleration graph. We're going to click on AY, acceleration Y component. And you might notice that as we go up in these quantities, we go from position to velocity and velocity acceleration, the graphs are getting worse. That's because Tracker's really only capable of measuring the position, right? When it makes these marks, it's marking out the position. When it calculates the velocity and the acceleration, it's taking the slope of the position and then the slope of the slope. And so every time you go up in slope, you're getting a little bit more error. So we'll talk about that later when we come to compare these. But right now we've got our acceleration value This is times 10 to the second power is the scale, so it looks like we might be getting pretty close to negative 10 here. But let's withhold judgment until we get to the analyze. Again, right-click on the graph, left-click on analyze. And again, we've got some leftover data that we don't want. So we're going to deselect these checkboxes so that we can't see the velocity. Again, it's very important that you do that so that you don't get yourself confused over what data set you're looking at. And for this one, we don't even want a line because this is supposed to be flat. This is supposed to be constant acceleration. So I should be getting a slope of 0 here. So this slope is actually misleading me a little bit because I'm giving the computer too many parameters to play around with. I want this to have a constant value. And actually don't have a fit for a constant value because that's located up here under Analyze. So now we're going to click on Statistics. So instead of looking at the curve fit, we can even deselect that and get rid of it. We're going to click on Statistics. Statistics is where we get information like what is the maximum value of this data set? That's going to be this point up here. What is the minimum value of this data set? That's going to be this point down here. I don't really care about that max and min because those are exceptions, right? That's from some calculation error. That's from video render error. What I really want is the average. I want to know what the average value is that all of these data points are oscillating around. So let's maximize this so we give a little bit more room here. So what I want to look at is the mean. I want to look at mean as another word for average. So I come over here to my acceleration. And I see that my mean value, my average, is about negative 1.7 times 10 to the 1. So I come over here, and my acceleration from the acceleration graph is equal to about negative 17. And this is where we want to start to look and compare these values because here I had a negative 10, here I had a negative 10.5, and you might have been worried, oh no, my numbers don't match. Well, these are pretty close compared to this negative 17. So it's at this point we have to take a step back and look at how we got each of these, right? This came from a parabolic fit of the original data. This came from a linear fit of some calculations based on that data. And this came from an average value of a calculation from the calculation. What I'm getting at is that 9 times out of 10, this value from the position graph is going to be the best option. You should still get an acceleration value from all 3 graphs because, number 1, you have that opportunity. You should go ahead and take it. Number 2, it's good practice. But number 3, it's good to see how those values compare and get an idea of how far off they are. But basically, we're probably gonna side with this value from the position graph. So we're gonna go with a negative 10 here. If I were writing up a report on this, I would report the negative 10. I would report that this value gave me good agreement, which is excellent. And I would report that this value didn't give me good agreement, but it's to be expected that this is gonna be the worst one of the group just because of all the calculations that have to go into getting these data points. One other thing I'd like to show you before I go, I'm back here on the position graph. You will likely want to include a picture of your graph in your lab write-up. And so the way to do that is just click on Edit, click on Copy, then click on Image. That's going to take this image here, it's going to put that onto your clipboard. So then you just need to go to a program like Word or Paint and press Control-V, and it will paste that image in. This will work in Word, this will work in Paint. This should work in your email, depending on the email client you use, but this is just a quick, easy way to get a picture of this nice graph and nice data fit that you've got for your lab write-up. So I hope that's been a helpful video for you, learning about 3 different ways to get acceleration from your data in Tracker. Next time we're going to take a look at how to program in our own quantities that we want to graph, like potential energy, and we'll see how to do that. So thank you so much for watching. I will see you next time. Bye-bye.